Okay, welcome everyone to the ISR Distinguished Lecture. It's my pleasure to welcome you. My name is Dick Taylor, and I usually often give a very short intro to speakers, but today I'm going to take the privilege of giving a little longer intro because I have a little longer relationship with our speaker today. So at lunchtime over pizza with a number of the students, I remarked that 1976 was a very good year for me. So that was the year that I met my wife, that was the year that I met Lee Osterweil, and also that was the year that I met Michael Gorlick, one of my current PhD students. So Lee and I have worked together for a very long time. We have seen our children grow up together. I've seen him move all over the country. He was here as chairman of the department of ICS back in, was it 89 to 91. We worked together at Boeing. We just had a very long and very pleasant collaboration. But I don't know if you read the little blurb about Lee in the flyer about this meeting here. But if you had, you know that Lee has received virtually every accolade in software engineering there is to get. So we got the ACM SIGSOFT Distinguished Research Award, the ACM SIGSOFT Distinguished Educator Award. He's an ACM Fellow from 1996, I think, probably. 98. So that goes way back. His paper at ICSI number 9, Software Processes or Software 2, is one of the most highly cited papers in the history of software engineering, and became the most influential paper of ICSI 9. So there was only kind of one award in the software engineering pantheon that he didn't have, which was the Distinguished Service Award. And you'll notice that is not on this, because this came out before the Distinguished Service Award was announced for this year. And Lee is getting the ACM Distinguished Service Award, which will be given to him in Hong Kong. And this
Hyderabad.
Oh right, right, Hyderabad.
Right.
And this award will help him towards one of his lifelong goals, which is becoming a 3 million mile flyer. So, what can I say? Lee's research has spanned from software testing and analysis tools. That's kind of how he got his start. That went on to software environments, and that led to work in software process, for which he is probably best known. And with that, please welcome Lee Osterweil.
Thank you, Dick. Obviously, I'm delighted to be here. Irvine is one of the places in the world where great software engineering has always been done and continues to be so, and much of it is due to Dick's tireless work to build the software engineering community here and in the world in general. So thanks so much for inviting me. Okay, so you've already heard about my interest in processes, and I'm interested in precisely defined processes, and I want to tell you something about why that is and the time that's available to me. I will try to use the plural singular, the first person plural instead of the first person singular, because almost everything that I'm going to talk about has been done in collaboration with a lot of other people. So here you have the faculty and staff level people who have collaborated with me, most principally Lori and George, but also Barb Lerner. Sandy Wise has been responsible for the language I'm going to describe, and then the list of students goes on and on and on. So I will try to use the word we a lot. We are interested in what we call human-intensive systems, and these systems go by a variety of different names, but the key characterization of these systems is that they are highly collaborative systems where the collaborations are among people, devices, and software. So sometimes the way I describe it is that these are systems where people are in the box, not outside of the box. So we rarely talk about users of our systems, we talk about participants. So these are systems where people are responsible for doing important parts of the work, but machines and software are responsible as well. And much of the challenge in these systems is to decide who does what. Humans should do things that are appropriate for them, and machines should do things that are appropriate for them. And they're getting very, very complex. They are getting to control almost all of the important jobs that are done in the world. And increasingly, our concern is that they're not as reliable as they should be. They don't work as well as they should work. And they are prone to failures. And when the failures happen, they can be catastrophic. So here's some examples of these kinds of systems and processes. Elections is the first thing that I'm going to talk about. And I'll tell you the way in which we regard it as a human-intensive process. We're also heavily focused on medical procedures. And here I have just two examples, blood transfusion and chemotherapy. But in fact, we're now starting to work with a Harvard Med School heart surgeon, and he's interested in the processes by which he does heart surgery. And then other areas, which would be regarded as human-intensive, software development. This is the original focus of the work I'm going to describe, was coming up with a way in which you could guide software developers to do software development better by a collaboration of the kind I described. And because of a lack of interest in the software engineering community, we've gone and talked to doctors and lawyers and election officials and so on and so forth. So I do want to say a couple of words about software development as there is time at the end. Hopefully there will be. But mostly what I'm going to do is talk about elections and medical procedures. So what is the approach? These human-intensive systems, we call them processes, are collaborations among all of these different kinds of agents. And what we propose to do is to model them rigorously and precisely, then to analyze them using rigorous analyses, analyzers like model checkers, fault tree analyzers, and so on, and then using the results of those analyses to do continuous improvement. So the big idea is continuous improvement of these very critical processes, which are collaborations between people and devices. So here's an example, healthcare process engineering, which is something we started to do about 10 years ago. There was a very famous report that was published in 1999 by the Institute of Medicine that estimated that 100,000 people a year die in American hospitals from preventable medical errors. And by preventable medical errors, I mean things like having the wrong type of blood transfused into a person, the wrong medication being given, the wrong lung being removed, things like that. Not doctors getting the disease wrong, just silly errors like that. And this doesn't count pain and suffering, and it doesn't begin to measure the amount of dollars. This is 100,000 deaths a year. New York Times published an article, this was several months ago, which confirmed that that was probably a serious underestimate. And the New York Times estimate was it was more like 440,000 avoidable deaths per year. Typically, if you compare these to other things, traffic accidents are about 1/10, 45,000. So this is probably the third leading cause of death in the United States, preventable medical errors. If you take 100,000 divided by 365 days, you get about one fully loaded Boeing 747. So if you think about one fully loaded Boeing 747 crashing and burning, killing everybody on board every day of the year for 365 years, 365 days in the year, then you get a sense of how much death should be attributable to medical errors of this kind, and a sense of why this is really, really important. Other example, elections. Elections you may think of as I put my vote in the box, and what's the big deal? But election processes really start way back at the beginning, where legislators vote about the characteristics that voting machines should have and the qualifications that voters should have, and so on and so forth. And they go through the long process of the casting of the votes, all the way down to recounts and court disputes and so on and so forth. These are extremely complicated processes, and they are also very varied. So the way in which I cast my vote in a small town in western Massachusetts is different from the way it's done pretty much everywhere else in the country. But there are some underlying similarities and underlying constraints. So nobody can vote more than once, no matter where you vote. Nobody can sell their vote, which means nobody will ever get a tangible representation of what their vote actually was. So those are properties of elections, but then the processes for the elections vary very considerably. Okay, so the approach, continuous process improvement, create a precise, accurate model of a real-world process, use formal analysis to automatically identify things like single points of failure, modify the process to address the problems, verify the modifications make things better, iterate, eventually deploy the process, iterate, so on and so forth. And especially in the area of elections, we expect the iteration goes on forever, because after you find a vulnerability and fix the vulnerability, then fraudsters who are going to try to undermine the election will become more clever and create more complicated kinds of conspiracies and so on. So we expect that this continuous process improvement idiom is something that will need to go on forever. So the need for precise, accurate models and the need for formal analyses will also be fixed and invariant. Okay, so process programming languages are languages which are effective in capturing and defining these kinds of processes. And the ones that we're interested in are things that have enough power to capture all of the complexity. And I'll get to a slide a little later on that gives you a sense of what the complexity is. But precisely define semantics. Since we want to reason about these things, in addition to having something that has a lot of semantic breadth, it needs to be something that has a lot of semantic depth as well, so that the utterances and the expressions in this process language can be parsed and analyzed. And then in the end, if a bunch of experts understand the process, but the domain experts, or a bunch of computer experts understand the process, but the domain experts don't, then there's something kind of lacking there. So in the end, we need doctors and nurses to understand the medical processes. We need election officials to understand the election processes and so on. So this is really quite a stretch to come up with a language that is broad enough, precise enough, visual enough, and so on and so forth. And it's been something that we've been working on for a couple of decades. And we finally have one that I think actually works pretty well. So I'd like to tell you something about it and what we've done with it. Basically what we've done with it is we've put this language, which we call Little-JIL, right in the middle of a number of tools and the kinds of results that the tools produce. So based on these process definitions and the expressions of properties, we can do model checking. Based on expressions of hazards, we can do fault tree generation. Based on scenario specifications, we can do discrete event simulation. And each of these things produces a different kind of diagnostic output. And given the reports of defects, vulnerabilities, inefficiencies, and so on, they are then fed back into this improvement loop. And this is what we've actually started to do, and I can give you some anecdotes. So for a starter, let me tell you about what we've done with the flavors model checker. But before that, I want to tell you about the Little-JIL Process Definition Language. Okay, so at first we thought that a language for defining processes was probably going to be relatively easy. And then when we started digging into it, what we discovered is that the language turned out to be very difficult, requiring all of these things. So I don't want to read you the entire list. Just suffice it to say that it needs to support reactive control, it needs to be concurrent, it needs to specify resources, it needs to specify something about timing, because most processes are timing critical, it needs to be rigorously defined, it needs to be a visual language, on and on and on. When we as a community started producing this specification, list of properties of this language in the late 90s, there was a large community that was interested in this work. Within 5 years, the community had pretty much dissolved. And my own pessimistic view is that when people got a look at how hard this was, they decided that there were easier things that they could do. But some of us were stubborn and we kept on. So the central abstraction of Little-JIL is something we call a step, and I don't want to tell you about all of these things now. I think what I'll do is I'll tell you about these characteristics of the language or of this particular abstraction in the context of the first example domain, which is elections. So we've used the Little-JIL Process Definition Language, which consists of a coordination diagram and has all of the things I talked about before for handling concurrency and exceptions and so on and so forth. It is visual, and we've used this to capture election processes in 2 California counties. So we've been working with Matt Bishop, who's at UC Davis, and he is an expert on the Yolo County election process, so we have now captured it in detail. And we've also worked with Elaine Janold, who is the Director of Elections for Marin County, and we have captured that process in some considerable detail. So the processes turn out to be enormous, and I obviously can't put all of it up there, but I do want to give you an indication of how this diagnostic game works. So here is a very high level of one part of the Yolo County process, and this is the pass authentication and vote part of the process. So this is right out of the middle. It happens on election day when you, the voter, come to the poll and wish to cast your vote. So this arrow says that the sub-steps that are listed below are to be executed in order from left to right. So left to right, first, the voter presents his or her ID. There is a pre-vote authentication process, which I'm going to elaborate in a bit. Then the voter is checked off as voted, the ballot is issued, and there is a recording of the voter preference. Each one of these things has a great deal of elaboration. And that's the way to think of this language, as being essentially a hierarchical elaboration language. And it's best to think of these steps not as sort of workflow steps, but as procedures that call each other, where the procedure calling goes from the top down, and this icon on the left side of the step bar gives some indication of the order in which the steps are to be done. So in this case, the order is from left to right. But now, when I elaborate this step, there's an equal sign, and that says that these steps can be done in any order. So these are concurrent steps. So pre-vote authentication consists of doing three things: confirming the voter ID matches the voter. So in some states, you have to present your identification. Maybe it's a driver's license. This is now politically very highly charged. In my precinct, you don't have to do that. Then you have to confirm that the voter ID matches the voting roll. So in addition to me being me, I need to have my name on the voting roll. And then you have to confirm the voter has not voted before. So these are the three things that have to be done before you can check off the voter as voted and issue the ballot. Now the way it works is that if some of these things are not satisfied, the voter is given a provisional ballot. And then there's a whole long protocol for how provisional ballots are dealt with. But the way we represent that in Little-JIL is with exception handling. So what we've observed about processes is that almost all processes in the real world are exception rich. And in fact, when we talked to a nurse at one point and we said, do you ever have any exceptions in the execution of your processes? The nurse said, exceptions are my whole life. So this is a failing of most workflow and process languages, that they will talk about the nominal way in which things go. I do this and this and this and this, like a pilot checklist. Check this, check this, check this, check this. But then if something can't be checked, if something is incorrect, then there's some kind of fix-up procedure off to the side. And an integral part of every process is what are those exceptions and how are the exceptions handled. So in Little-JIL, every step may have one or more exception handler. The handlers are steps themselves with full decomposition and full parameter flow. They react to exceptions that are thrown in descendant steps, which says that the scoping in Little-JIL, the exception handling in Little-JIL is scoped. Steps can have pre and post requisites, which are responsible for throwing the exceptions, or the agents can throw the exceptions themselves. And then there are 4 different continuation semantics, which I don't need to get into. So a fuller view of the process looks more like this. So now present ID can throw the missing ID or the inadmissible ID exception. Confirm voter ID matches voter can throw the ID mismatch exception, and so on. And here we see the 4 exception handlers that are up at this ancestor step. And what this one says is the missing ID exception check basically says, consider this step done and go on. This one, same thing, admissible ID exception, go on. ID mismatch exception, go on, but voter has already been checked off as having been voted. There is an exception handler for that, and that is fill out provisional ballot and basically submit the provisional ballot. So that says basically the voter presents the ID, and if these things all check out, but the voter is checked off as already voted, then the voter gets a provisional ballot. So that means Isaac comes in the morning and he says he's Lee Osterweil, he gets given the ballot, he votes. Then I come in later in the day I present my credentials and they say, it looks just like you've already voted. I have a fit on the screen and they say, here is a provisional ballot. And then the provisional ballots go into a separate hopper. So the question is this an appropriate representation of the process as it should be? So that's what we are attempting to do with these processes, is to take this definition and do analyses to see whether these processes satisfy the properties that they are supposed to satisfy. In this case, the properties come from the law. And the law says things like no voter can vote more than once and so on and so forth. So in addition to creating the process representation, we also create a representation of the desirable properties. So that requires us to refine the high-level requirements for a process into low-level requirements and precise properties that consist of event sequences in an event alphabet. Then we take this event alphabet and we annotate the process graph with the location of the steps at which the events in the alphabet take place, and then we do basically finite state verification, model checking. So here's an example. Each unique voter is allowed at most one vote. That decomposes into most voter must be authenticated before entering the voting booth, and on and on and on. And this is the one that I want to check. The voter must be authenticated before entering the voting booth. So we have a system called Propel, which Laurie Clark and George Vrunin built, and I don't want to tell you all the details about Propel, except that at the end, it produces a finite state machine, which is the encoding of that property. And then the question is, can we trace all the possible paths through that process and run the events that we encounter through this machine, and at the end, see whether the machine winds up at an accepting state or not. So we build the finite state machine, we take the Little-JIL process definition, we annotate it with the events, we give it to the flavors finite state verifier, and in the end, it discovers a violation. So it turns out that that process is defective. So you all looked at it, and I went by it kind of quickly, and I didn't give you enough time to think about it a lot, but it turns out that there's something wrong with that process. And what's wrong with the process is the fact that this is a parallel step when it should be a sequential step. And as a parallel step, what it says is these things can take place in any order. So if I do this step first, then this exception is thrown and the voter gets the provisional ballot, and then maybe it's sort of like, well, wait a minute, this voter is not on the voting rolls. And that should have caused the voter not on the voting rolls exception to go on without the ballot being issued. So it turns out that there's something of a race condition here, and the race condition matters. So this was not a contrived example. We actually wrote that process, we looked at it, we thought about it, and it looked right to us, but the analyzer determined that it was not correct. So here's the violation, present ID, do this step, get the ballot, poof. And this is the explanation. Parallel step creates a race condition, pre-vote authentication is executed in parallel with two others, exceptions can take place in any order, yada, yada, yada. So this is an example of the kinds of diagnostics that we do. So at this point, sometimes people say, but wait a bit. This obviously is not going to happen in real life. You're going to come into the polling station, and a human being is going to be sitting there and is going to be doing all these things, and nobody's going to let this happen. So I guess my answer is yes, but. And the but is, in the end, we are moving towards more automation for all of these processes, certainly for elections. So at some point, probably these things will be automated. In fact, we're now talking about electronic balloting, e-voting. And it's headed our way, and it's fraught with all kinds of perils. And in the automatic e-voting process, these things will all be done by some computer, and the order in which the computer does them actually matters. So in fact, we did discover a defect in the process. If human executes that step, maybe it's okay, but if the step is executed automatically, this is a defect, then it needs to be fixed. So this scenario actually could happen, would probably manifest itself as a bug, and there would have to be some process improvement after this bug was detected. Our point is, model the process, do the analysis, and do the improvement before the bug actually happens. So nowhere does that seem to us to be more important than in the medical domain, where these bugs actually can cause death. So in the medical domain, our most famous example was finding deadlock in a blood transfusion process. So this was a blood transfusion process that we had faithfully copied down. We validated it by checking it off with the docs, and then we discovered a deadlock. So like, how could this possibly be? And the deadlock was the simplest kind of a deadlock imaginable. The doctor calls down to the blood bank, or the nurse calls down to the blood bank for a unit of blood. The blood bank calls up to the nurse and says, we need the blood type, do a type and screen, and the nurse is waiting for the blood bank is waiting for the nurse to come up with a type. Deadlock. Easy, easy deadlock. So we went back to the domain experts and we said, there seems to be a deadlock and that can't possibly be because real processes in the real world obviously don't have deadlocks. And the reply was shocking. The reply was, my gosh, that actually happens. We see that from time to time. So like, well, why have you not fixed it? And the answer is, because it only happens on rare occasions and we've never been able to figure out the circumstances under which it happens. Can you help us? So with our analyzers, we're able to trace the sequence of events and said, here's the sequence of events. It was an unusual sequence of events, but there are hundreds of millions of blood transfusions annually in the United States. So this happened with predictable regularity. And they said, thank you so much for finding that defect. We will now go off and change our process, which they did. And we asked them, could you please tell us what you did to fix the process, because we'd like to do an analysis to be sure you got it right. No worry, we're sure we got it right. Could we please look anyhow? So we looked, and in fact, they had removed the deadlock. And in its place, they had inserted a race condition, a dangerous fatal race condition, which was just proof to us that the processes that people are performing now in critical kinds of situations are so complicated that the performers have lost their grip on them. All the more reason why this sort of thing needs to happen, because the performers of these processes really do need guidance, and the processes need to be fixed. So we've found race conditions, we've found unsafe sequences like administering medication without checking dosages, without checking for permissions, not being sure that patients' weights are properly performed, especially in chemotherapy where patients lose weight over time. It's important for the weight computation to be accurate and kept up to date. Sometimes it doesn't happen. Letting patients into the emergency department without wristbands or with multiple wristbands. Sometimes patients will have 2, maybe 3 wristbands from previous admissions and from admissions to other hospitals and so on. So, Finite-State Verification and model checking looks for event sequence defects, but it assumes that all the steps are performed correctly. And now at some point somebody came to us and said, but we all know that some of the steps in many processes are not performed correctly. And if that's the case, your analysis would seem to be not as useful as it ought to be. So that caused us to investigate fault tree analysis. So fault tree analysis is a well-accepted practice. It was pioneered, I believe, by the Defense Department and NASA. And fault tree analysis basically starts out with a hazard, which is a condition in which the loss of life or serious loss of property is a possibility, and it traces backwards to see the circumstances under which the hazard could arise, assuming that the hazard will arise because of the incorrect performance of one or more steps. So this is another kind of analysis that we perform. We take the process definition, we take a specification of a hazard, we put the two of them together, we produce some failure modes, we do fault tree analysis, and see if we can do improvements that way. Okay, so this is a picture of a fault tree, and this is automatically generated by one of our tools. And at the top we have the fault, or the hazard, and below it we have a combination of AND and OR gates. So these blue ones are OR gates, the pink ones are AND gates, and what we read off from the bottom are the primitive events, and these would correspond to steps in the Little-JIL process that were performed incorrectly, and then this gives you the sequence of ANDs and ORs which put together cause a hazard to take place. Hazard at the top, gates, primary events. Having done that, what we can do is produce things called minimal cut sets, MCSs. And a minimal cut set is a minimal set of primary events, all of whose occurrences together ensure that the hazard will occur. And the MCSs are very easily computed by using straightforward Boolean algebra on the fault tree once the fault tree has been built. So an MCS indicates a system vulnerability, and the vulnerability is the incorrect performance of the step. And there are at least two kinds of misperformance. Some is carelessness, or the lack of ability on the part of the performer. And some of it, in the case of elections, might be attributable to somebody actually attacking the process by purposely doing something wrong, taking the ballot, putting it in the wrong box, whatever. A singleton MCS is called a single point of failure, and that's particularly worrisome. So our approach is to generate these fault trees automatically from the process definition. So previously we had taken the process definition and we had built a flow graph upon which we performed model checking or data flow analysis. Now we take the same flow graph and given a hazard, which is an event which we are trying to avoid, we can automatically generate fault trees. And from the fault trees, the minimal cut sets. So here's an example of something which is a little more real. And here's another example drawn from the medical domain about blood transfusion. So here's a blood transfusion process, and it starts out by obtaining the patient's blood type. This is a tri-step. It says first try to get the blood type from the lab, and next get the patient's blood by testing the patient's blood. Either way, the blood type goes to the blood bank where the blood is picked up and the transfusion is performed. So the question is, how robust is this process? How resistant is it to the misperformance of a step by a single performer? So we build the fault tree, which looks like this. We calculate the minimal cut sets, which look like this. And what we note is that there are two singletons, step E4, you probably can't read this, and step E11. E11, patient ID to blood transfusion process is wrong. So this says if the blood type is communicated incorrectly, then the hazard of an incorrect type of blood being delivered to the patient will happen. And E4 is something similar. So just in case you think this looks like you might try to do it by yourself by hand, this is what the real fault tree looks like. So in fact, the way fault trees are built now is by what's called box set technology. Box set stands for a bunch of guys sitting around a table. And that's basically people sitting around thinking very hard about all of the ways that things can go wrong. And you can see that this is very vulnerable to just one or two of these edges or nodes being wrong. So this is a very dicey way of doing something very important. So generating these fault trees automatically from a rigorous definition, like the Little-JIL process definition, seems to us to be a really good idea. Okay, so that's something else we can do. Fault tree analysis. The other thing we do is discrete event simulation. So from the process definition, we can drive model checking, we can drive fault tree analysis, we can also drive discrete event simulation. So we now have a discrete event simulator that takes Little-JIL process definitions and builds discrete event simulations. And here is a simulation. This is a representation of the way in which an emergency room works. And in fact, this turned out to be a very much trivialized version of how an emergency room works. And then we take specifications of the resource types, because this is a domain where the resources become extremely important. So in the earlier examples, the nature of the resources maybe didn't seem like they mattered much, but in an emergency room they do. So an emergency room is a favorite area for discrete event simulations because it's so difficult. You have nurses, you have doctors, you have orderlies, you have beds, wheelchairs, medications, x-ray machines, and on and on. And what the emergency room management is typically interested in is moving people through the emergency room as quickly as possible. Except what we discovered when we actually interviewed people about what they were really interested in, it turned out, no, they were actually really interested in making money. Because it turns out that in most hospitals, emergency rooms are cash cows that are counted on for heavy revenue flows. So they want to make money. They want to move patients through quickly. They want to have enough doctors so that people move through quickly, but not so many doctors that they're standing around getting paid too much money and so on and so forth. So it's a very highly constrained optimization problem. And the core of it is, how many nurses do you need? How many doctors do you need? And what strategies will you use in order to optimize the way in which they work? So the process definition, very important, but the resource specifications, also extremely important. So Little-JIL incorporates a capability for doing a tremendous amount of detailed specification of the resources. What capabilities do the resources have? What is their expertise level? What shifts do they work? Under what circumstances can unusual things happen? So it turns out that nurses can prescribe heart medication under some circumstances. And the circumstances are usually pretty well spelled out. No doctors are available, the patient's about to die, so on and so forth. Doctors never administer shots. It's beneath them. Except if there are no nurses available and the patient is turning blue and dying, then the doctor will administer a shot. How do you take all of that information? Well, you build the process definition and then you build the resource specification. And having built those things, now you can actually run some simulations. So here's an example of one of the simulation results. So there's a couple of ways of scheduling medical personnel onto tasks. And this one is the sickest first scheduling policy, which says essentially that acuity level 6 people who are bleeding and dying of gunshot wounds get the attention first, and then acuity level 5, people who are having heart attacks, and all the way down here, acuity level 1, are people who are coming in for a flu shot. And what this box plot shows is that with this sickest first scheduling policy, the critical and the acuity 5 level patients get pretty good care, although there's a fair amount of variation, but the acuity level 1 people basically don't hardly get any attention at all. So we changed the scheduling procedure to something which is priority-based, that has something that has a lot more to do with the amount of time people have been sitting in the waiting room, and the difference is dramatic. Sickest first, priority-based. Sickest first, priority-based. So this was the first eye-opener. Then we went on and we looked at various other things, like whether doctors should take on patients during the last hour before their shift ends. This one is whether the same doctor should see a patient all the way through the patient's stay. And it turns out if the same doctor is required to see the patient, then the waiting time is a lot larger than if different doctors can see the patient. This was intuitive, but this simulation actually gave us quantification. So we found a lot of defects in healthcare processes. This is something we're very proud of. Our partners at Baystate Oncology Division in Springfield, Massachusetts, have been measuring the number of errors that reach patients for a number of years. And in the 2 years following the introduction of this process thinking, the number of errors reaching patients was reduced by 70%. So this has now appeared in a medical journal, and it's one of the things we're very proud of. I really want to talk about software development, so I'm going to go through this really, really quickly.
Lee, you got plenty of time.
Okay,
Okay.
great. Software development. Like I said, this was what I thought we were going to do with this originally, and then long ago when we first started talking about this and said, we're going to show software developers how they should actually do software development, it was sort of like, this was a no sale. It was like, no way you're going to tell software developers what to do, because software developers are quintessential artists and people who are divinely inspired. So we did much better with doctors who were willing to believe that they had things they could learn about processes and lawyers and so on. But now we're finally getting around to software developers. So one of the first things we've started looking at is Scrum. So everybody knows what Scrum is, except basically it turns out that sort of nobody knows what Scrum is, because there's really no definition of Scrum. So what better mechanism for being specific about Scrum than to take a rigorously defined language like Little-JIL and producing a Little-JIL definition of Scrum. Now, it may not be the Scrum that you actually are doing, but it might be a Scrum about which we really know something. And people might like the idea of accepting the discipline of some particular Scrum if they know what advantages and disadvantages it has. So what we've done with the Scrum is we've produced some precise definitions, and we've done some simulation of task assignment strategies, and we've gotten some results. And the other thing that I've always been very interested in, and it was one of the last things Dick and I talked about when I was still here, was rework. What is rework? So I'm going to give you an example of what rework is if I have time. So here is a Scrum in Little-JIL, and I'm going to go through a bunch of slides very quickly because you don't want the details. So a development iteration consists of a sprint planning meeting followed by a sprint, followed by the sprint review with pre and post conditions and a sprint retrospection, and elaborating the sprint. Sprint is 30 instances of daily sprint, and that's in parallel doing the daily Scrum, doing check work and revising the sprint backlog. And check work looks like work, integrate, and rework. So at some very high level, that's what the Scrum, what a sprint consists of, and that's how it fits into the whole development process. And we discovered a bunch of things that people thought were true about Scrum that probably were really true. So for example, the idea that the sprint team was the only one who could change the burn down list, yes, we can show you in the process exactly where that comes in. But now, what we've wondered is whether it matters, whether there's a strategy for taking tasks down off the burn down list. So we hypothesized a distribution of task sizes and difficulties, a distribution of worker, coding, and testing skill levels, different team makeups, different team sizes, different strategies for task assignment, and then we took a fault injector, and we have a fault injector that injects into the actual simulation incorrect results according to distributions to simulate coding bugs and inadequate testing, and then the idea was we would iterate until no more bugs were found. But bearing in mind that some of the bugs that we had injected because of failures in the testing process maybe did not get detected. So now we have some code that has some bugs. And then the question was, what strategy should be used in assigning tasks in the Scrum? So we started out with random assignment of tasks to workers, where any worker just sort of randomly took any task. Then there was the greedy assignment strategy, where the hardest tasks were given to the strongest workers. Then there was the prev. So there's this idea that there's a big task and it's on the burn down list, and somebody takes it down, makes some progress with it. The day ends, the task gets put back on the burn down list, and who gets the task the next day? Should you favor the person who didn't finish the day before, or should you favor somebody else? Or should you let the same person retake the task for 2, 3, n days before you give it to somebody else? That's prev. And then greedy prev is a combination of the two. And what we discovered is that different task assignments really mattered. So these are all comparisons of the random strategy, and it shows that the greedy strategy actually does at least twice as well as measured by, what is this? I think that's the team consisting of 4 of each. And, but the prev strategy does even better, and the greedy plus prev strategy does better still. And I think most of the results seemed intuitive, but the actual numbers were a bit surprising. So the fact that these numbers for teams consisting of 6 programmers and 2 testers were not nearly as good as for teams that consisted of 4 programmers and 4 testers. And we have a number of other results like this. So we're starting to look at Scrum. What is rework? What we've discovered is that rework is probably a fixed thing in any creative activity. So we've discovered that ecological scientists we work with at Harvard do rework. Doctors do rework when their diagnoses don't work out. Labor management negotiators do rework when they discover that the compromise they suggested doesn't work out. And software developers always do rework. In fact, if you ask most software developers what they do most of the time, they will mostly say they do rework most of the time. So what is the nature of this rework? What does it actually look like? So the hint, rework is basically recursion. And here's how it looks. If development consists of doing requirements, high-level design, low-level design sequentially, and you notice that there's no way that rework involves going back. So in fact, rework doesn't involve going back. So let's take requirements and let's decompose it. And here is rework in A, not D, A requirements process. And it says requirements is the parallel activity of cleany plus number of developed requirement element activities, which consists of declare and define requirement, declare the requirement, define the requirement, and then post condition that says requirement is okay. So this post condition check is some arbitrarily complicated thing, and if this succeeds, in other words, if it says it's okay, then you go on, but if it doesn't succeed, then it throws this exception, and the exception handler is develop requirement element, which is a recursive call to this. And that says basically go back and do it again. Except it's not a loop, it's a recursion. So this language, Little-JIL, has a first-class notion of abstraction. So what this says is that this causes the reinstantiation of this now in the context of the exception handling event. And that says that develop requirements element consists of doing these steps, but in the context of knowing that it's been done before and that there's been some problem that's been discovered. And of course, you can recurse again and recurse again and recurse again, always carrying this deeper context. Same thing in design. Here's high-level design. Develop design elements. Declare design elements is the parallel cleaning plus excuse me, instance of declaring design elements. But now there is a design requirements conformance check over here. And the design requirements conformance check basically says the design elements that you've designed, do they correspond to requirements elements? And if they don't, then the exception is thrown, and this is a missing requirement exception, and it causes add new requirement element. So this is rework. So rework, as it's glibly described, is going back to a previous phase, but we're not going back to the previous phase, we're doing a high-level design. But in the context of high-level design, we are now adding new requirements elements. And add new requirements elements consists of defining a new requirements concept and doing declare and define requirement. And if you remember, declare and define requirement came in the previous requirements process. That's where it was originally seen and where it was originally defined. And now it's being instantiated here in the context of add new requirements element, which is in the context of develop design elements. It's during design. So rework is the recalling or the recursive instantiation of something that you did before, but in the current context. And this language and this representation makes it very clear. So here is the invocation of the step originally defined in requirements. The same exception is thrown, but now, because it's in a different context, there is a different exception handler. And this is exactly what rework is. So we're very pleased at this view. It causes us to basically produce specifications of sort of waterfall kinds of software development where there's lots of exception handling that causes the re-invocation of things from previous domains in new context, and that's what people are doing when they do rework. I can't resist preaching a small sermon. So Dick mentioned the famous paper, Software Processes or Software 2, and most people understood that to be, if you're doing the development of software processes, in fact any processes, it would do you well to think about what software developers know about defining real computer code software. When in fact the original intention was, no, both of those things are part of something greater, and each one can learn from the other. So what I've spent the previous 40 or 45 minutes explaining is how a software engineering view can help us to do better with processes. But how about going the other way? Is there anything we've learned about processes that could help us to be better developers of application software? And in fact, I've got two things. One is resource management. So in fact, it turns out that if you look at modern programming languages, they say almost nothing about resources. And as time goes on, this is going to be a bigger and bigger difficulty because resources really matter. Who does something really makes a difference. Nowhere is this seen more clearly than in the cloud. So if you have some activity, some application, and you have to invert a matrix and you throw it up into the cloud, do you care who does it and what they did and how they did it? Of course you do. And that's exactly what this concept of resource is all about. We don't see it in current languages, but if we're going to learn something from process software, it is that resources matter, and it matters in application software as well. And the other thing is rework. So rework is a constant. Any creative activity involves rework. And our understanding of rework is very dim. but it becomes sharper when you look at it in the context of processes which we all carry out, software development, fitting curves in science, and so on and so forth. So the learning goes both ways. And finally, the last thought. What we do as software engineers is much more fundamental than we think. If we think that what we do is write code to run on computers, and that's what it is we do, and that's what it is we know about, then we've given away a great deal of the power we have to make the world a better place. So what we know as software engineers is how to build these very complicated systems. And that means that we have learned a lot about abstraction. So people sometimes say to me, this language of yours, is this just a workflow language? And the quickest way of disposing of this are like, our language has abstraction, and workflow languages don't. So now think about a language with no abstraction, and now you know what's wrong with workflow languages. So we've understood what abstraction is, and we've put it to good use. We understand about concurrency. Is our understanding complete? No, it isn't. But it's better than what other domains have come up with. We understand the juxtaposition of analysis with synthesis. We understand phase development. We understand about evolution. There's a lot of things we as software engineers know and can apply in other domains. We can learn from other domains how to build human-in-the-box systems, how to do rework, and so on and so forth. So I guess what I'm saying is that one of the most interesting parts of what I've been doing for the past 20 years is seeing what the similarities are between process software and application software, identifying the differences and looking at what each one has to do with each other. And with that, since I've already run a bit over, I will be glad to answer questions. Yeah.
The way you've defined rework sounds a little to me like refinement. Can you explain maybe the difference or the similarities between rework and refinement?
Well, so this is not refinement. This is recursion. So basically, this is doing this step again, but doing it in another context. So refinement seems to me to speak more to the creation of more details that weren't there before. So this step already had a bunch of details, but these details are now plunked down into a deeper context.
Yeah, I mean, I think of refinement sometimes as a recursive process, right? Because you're sort of going back to saying, flesh this out.
Mm-hmm.
So.
The context turns out, from my point of view, the context turns out to be extremely important. And recursion, which is something we as computer programmers know all about, is a natural way of describing this thing which sort of is, I think, badly mischaracterized in the common mind, namely rework. It's going back and doing something again. Well, it's not really going back. It is reinstantiating something you did before, but now with some knowledge of how it turned out previously so that you can presumably do it better.
Have you had the chance to talk with people from change management, which they have to promote code from one environment to the other? And they have lots of checks and processes that you have to follow. Some are semi-automated, others are completely manual.
Nope.
This would be interesting.
Sounds like sort of what the world needs. On the other hand, what we really emphasize is that these things are important and more important as they are verified and they're better understood. So the application of analyzers to identify defects and to fix them and to do continuous improvement really seems quintessentially to be what this is about.
I love the concept of the recursion, and I would like to add a little grain of salt from a total outsider. Normally, an iterative process calculates what is supposed to be the best result that we know up to that iteration. The recursion implies not the computation. Implies not computing a final result because there is a realization that something else is missing and needs to be computed in a manner that is akin to the original computation.
Yeah. So there's a
So
whole
you're not arrive at a final result
That's
or
right.
what is the best guess at that point, but you to come to the realization that you need to do some extra work.
Yeah. So there's a whole part of the work we're doing now that I didn't even mention, and that's about provenance. And
Yeah.
provenance basically is the history
The
of
stack
where
that you
something
built,
came
yeah.
from.
Yeah.
So what's actually going on in the background here, so when I talk about carrying the context forward, nobody asks exactly how that's done. So we have something that automatically generates provenance as the
Mhm.
processes go. So now anything you point to as a current artifact in your process has a history, and that provenance history can be inspected and discovered,
Yeah.
and then that basically supports what it is you're saying. It can be used to suggest what still needs to be fixed and how it might be fixed, or at the very least, what you've tried previously.
Right.
So the automatic generation of provenance is probably one of the more important things that you're doing here. Just so much I could cover in one talk about.
It's very nice. Congrats, yeah.
Yes, sir.
Can Little-JIL handle multiple outcomes? For example, an ER optimizing for profit with, I guess, at some level of patient outcome?
So basically what it's doing is it's just running the simulations, and then you can attach these kinds of analyses at the end. So it is distinct from, so basically at present, all these things are offline. So none of these things are happening online. The simulations are all simulations. We run 1,000 simulations. We look statistically at the results, and we determine how well they do with respect to certain optimality targets. The way hospitals typically run is that some amount of this stuff is going on in the background, probably in the heads of the performers, and they are taking these objective functions into account when they do things like sending nurses home to save money or calling doctors in an emergency, and so on and so forth. So putting this stuff online so that actually driving things now starts to involve doing what you're talking about, namely taking objective functions that are weighted among a bunch of different desiderata and using those to drive things forward. So that we're not doing at present.
A related question, how long or how much training do you expect it to take for a project manager or a hospital director to be able to write out a project in Little-JIL?
Yeah, so never. What we have discovered is that the better hospitals have information technology people who are actually part of the team. So this is, we believe, the way things are actually going to go. So programmers write programs, optimizers do optimization. Medical people need to review these things, but not write them. So the way I put it is that we can have many people who are readers of software, but relatively few people who are writers. So everybody can read Shakespeare and can even appreciate Shakespeare, but only Shakespeare can write Shakespeare, right? So similarly, a lot of this stuff will be written by experts who can write it and do a good job of writing it. At that point, we expect the domain experts to be able to read it and critique it and identify errors with our help. But we do not expect medical professionals, doctors are never going to write this stuff. But the better hospitals now have IT staffs, and some of these people are quite good. So we started out working with our local tertiary care facility in Springfield, Massachusetts. We now have ongoing collaborations with UC San Francisco and with Harvard Medical School. So the better medical schools are onto this stuff, and they care about this, and they have very good IT people. So we believe that's the future. This is the kind of thing that those people will be responsible for.
So arguably, the initial failure of healthcare.gov was due to process errors. We use the term very, very broadly.
Yes.
And I know you were part of the National Academy of Sciences study of the Center for Medicare and Medicaid Services. Did your understanding of processes for them enable you to predict that? Or did that play any role, or was it just abject incompetence?
Almost everything that happened was warned about in our report. But then there were some things that happened that were beyond what anybody would ever imagine. So can you imagine a major system like that being rolled out on, being aimed for rollout on October 1st, when on September 15th, it had never been end-to-end tested, never. This is 15 days before the national rollout, and they had never end-to-end tested. Are you kidding me? So what our report said basically was the difficulty at CMS is that there was insufficient, there continues to be insufficient in-house expertise about software engineering to be able to make these top-level, really important decisions. So there were people there who said, seems like that ought to be okay. I mean, so the absence of that kind of expertise in-house was something we noticed and was warned about. So you've got to get smarter people in here to look at what your contractors are doing and saying, because some of the contractors were saying, that's just crazy, man, you can't do that. But in-house it was sort of like, well, you know, we promised the president and we're gonna roll this thing out. So yes, that would, I mean, I guess we could call that a process error. Deciding to roll out an important system when you haven't really tested it, really, in any real sense of the word, that's clearly a process error. Okay.
I need to ask a classical question. So you can model an awful lot, but what can you not model?
So it's an interesting question about how far this actually goes. So at the bottom, the leaf steps are steps that are bound on performers, and we basically at that point just sort of give the performers the task and say, you know, do this, however, without any advice. So a bottom level step might be, for a programmer, make a brilliant design decision. For a doctor, it would be make a crafty diagnosis. And we don't give people, this language doesn't give people guidance on that. There are other people actually who do. So there is another branch of the medical informatics community that's trying to take medical knowledge and distill it down to guidelines using rules and so on and so forth. So our language doesn't do that. The other thing it doesn't do is it doesn't work very well with directing the way in which humans will collaborate with each other. So Christoph Dorn was here as a visitor, and Christoph invented a language called HADL, Human Architecture Description Language. And Christoph and I are starting to write some papers together, and the essence of the paper is, at what point should the Little-JIL stop and the HADL pick up? So there's certain kinds of things that this stops at doing, and then the question is what picks up there, if anything, and how to mesh them together.
So you've had a lot of experience in working with different processes, as you've talked about, which very impressive. Can you share with us any insights you have with regard to sort of what you'll think of as meta processes? That is, so now that people are writing processes and experiencing faults in them, could they have done it better if there was some higher level process guidance that said, wait, if you're going to do a process, here are the things to think about first, or here are the that is there a process for the process of making these things?
Well, since they're all software, the process for doing this is the software development process. So like everything else, it needs to start with requirements. So what you're seeing here is, I would characterize this as an architecture language. I'd be interested in whether in architecture people feel that way, but I'd characterize this as an architecture language. So, it being a piece of software, you don't start with the architecture, you start with the requirements. So the question is, what are the requirements? And then you can architect a process. So the higher level thing is the thing that we already actually know something about, and that is the phase development activity. And if you buy that, then continuous improvement is what we know all about. Requirements, architecture, design, implementation, evaluation, evolution. So this is really just another idiom for the software development activity applied to this domain of processes in various disciplines, like medical, elections, labor management, negotiation. And in fact, when you become a process head, you see process everywhere. And almost everywhere you see process, you see something whose complexity is vastly underestimated. So I no longer believe that there is such a thing as a simple process. Almost everything you look at is enormously complicated, mostly by exceptions. And mostly what people are looking at is the nominal, and they say, well, this is a pretty easy when you do this, 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 and this. Like the checklist that a pilot goes through, it's check, 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 check. What's hard about that? What's hard is when something can't be checked. Now something has to be done, and you're off in some exceptional circumstance. And the bad accidents that happen when an exception arises in the handling of another exception, which arose from the handling of yet another exception. And when we interview medical people in particular, every time they say, okay, the next thing I do is X, and our students are now trained every time somebody says something like that, they say, well, what do you do when it goes wrong? And the usual answer is, oh, that's really complicated, you don't want to hear about that. And our answer is, if it's really complicated, we really want to hear about it. And then usually the domain expert winds off in the weeds somewhere. Sort of like, well, you know, we haven't really thought about that very carefully. It's like, exactly. That's why you need us. And usually the reason they haven't thought about it carefully is because they're using some sort of trivial workflow language which does not help them to describe something hard. But if you have a language with exceptions and first-class notions of abstraction, you can actually just describe and define the hard stuff, and sometimes very cleanly. And then very often domain experts look at that and they go, wow, there's more there than I thought, and in fact, unexplored areas.
Okay, one more question. Matthias.
Thank you. So many times these systems are supported by software, right?
Right.
And the software has also requirements. And my question is there a formal way to manage traceability between this model process and formal requirements?
So, okay, so something I haven't emphasized nearly enough is that there's nothing in this specification that says what the agent is, whether the agent is a human or machine. So there is a separate specification of the actual resources that are available, and when the simulation actually runs, the resource manager looks around for something which can satisfy the needs, and it may be a human, it may be a non-human thing. So there is a whole language for the specification of those resources and the specification of the way in which the resources are to be assigned. Now, when it comes to reasoning about things, we're in the same situation as you're with any other piece of software. So when you write a piece of software, you have higher level things calling lower level things, and some are out in the cloud and so on and so forth. Then the program you write does not have any specifications of what you're expecting out of those things. But if you want to prove anything about them, if you want to reason about them, then there needs to be a separate specification of the behaviors of those things. And the same thing is true here. So some of those specifications of those things are actually in the resource management facility, but not all of them. So this is another way in which what we're doing here is sort of suggesting ways in which the development of real application software could be improved. If you had a separate specification of the agents, the entities that carry out the steps, then that would be ready and handy to support the analysis that you want to do. And right now we write programs and these specifications don't exist. The programs simply run. And technological debts, the technical debt that's incurred by the thing which is accepting responsibility for doing a component part is not enunciated and unknown.
All right, please join me in thanking Lee again.